So this is our third lecture, and today we are talking about derivative and we will try to do step-by-step problems of optimization. So first lesson will be about math, and the second one will be actually the first lesson about something close to machine learning, because lessons before you've learned only about math and Python. So first we will start with derivative. So let's consider, first of all, let's consider linear function. We've talked about linear functions on our previous lesson, about the graphs, and about how to represent them with formulas. So this is our b, this is 0. And now let's introduce definition of slope. So slope of line is equal to difference in, it's equal to fraction of difference in y's and difference in x's. So what, for example, we will define our delta x, and then we can calculate delta y, and in that case calculate slope of line. And in fact, delta x, it can be represented in as x2 minus x1. That means that delta x, it depends on two variables, on x2 and x1. And delta y can be represented as or alternatively, and this holds for every function, obviously. So this is our definitions of delta x and delta y. And now let's substitute these definitions into the definition of slope of line and get our number. So slope, I won't denote with any numbers or letters, just write slope is equal to delta y and now we remember about this function, which is a linear function, and now we can substitute and find y for every value of x2 and x1. We can see that b is nullified, and we can see that actually this part is equal to k multiplied by x2 minus x1. Because our delta x is not equal to 0, which means that x2 not equal to x1, we can successfully divide both parts on x2 minus x1 and get that slope of line is equal to k. And in fact, as you can see, there is no x2 and x1. That means that the slope doesn't depend on x2 and x1. slope of line is constant for every extruent. And it's equal to k. Yep. That's pretty easy. And why do we need to consider the slope, and what is derivative, why derivative, and what's the matter with the slope? So actually now, after we've considered linear function, we can consider other functions which are more complex, and see how the slope of line depends in other particular cases. So I'll just write definition of slope of line, definition of any function, and I will write that slope of line is equal to k. So now we will try to do the same for other functions. This is our x1. Yep. And slope is equal to and in fact we can see that we can draw a line between these 2 points, and it's called secant, and we can see that slope of this secant, because it's line, and it's equal actually to slope of this function. So it's equal to slope of secant. However, this slope of just any function which is not linear or constant is not very useful for us, because it depends on x2 and x1. Because, for example, take a look at quadratic function. So our slope, let's calculate slope and see if it depends on x2 and x1. We can use this special formula to make our slope simpler, and as we can see, it actually depends on x2 and xy. So if we take very big x2 and xy, then obviously slope won't tell us about local behavior of function. So we would take, like, this is our quadratic function, and if we take opposite points, then slope of this line will be always equal to 0, and it won't tell us anything. That's why we will consider what will happen if we will constantly make x1 and x2 closer and closer to each other. So what will happen if our x2 is getting closer to x1. And let's talk about this example. So in that case, we can write down that x2 from this definition of delta x. We can write that x2 is equal to x1 plus delta x. And because x2 is getting closer and closer to x1, we can see on number line, this is our x1, this is our x2. So this is our first, then this is new x2, this is new x2, and then it's getting closer and closer. And distance between these 2 points is equal to delta x, and delta x is actually getting to 0. So now we can substitute this equality here and get that it's equal in fact to delta x1 plus delta x. Yep. And if x2 is getting closer and closer to x1, that in that case delta x is getting closer and closer to 0. And in that case, this slope is getting and getting closer to 2x1. So there we get that slope depends only on x1. And what will happen with graph, what will happen with second of this function in this case? Let's see some graphs. So this is our linear function. We get the slope is equal to k. And if we are talking about, so we talk about second, which is just a line between points y1, x1 and y2, x2. If our x2 is getting closer and closer to x1, then we can just denote as x1 as x. And in that case, we will not get second, we will get tangent line. So tangent line has the property that in this point, it touches the graph, and it's the only point in which it touches the graph. So in this point it touches, and then it gets away from this graph. And here we write the same for just function f of x. And now let's see what will happen if we make it smaller and smaller. So this is our sum function. I took for this example it's a sine function, if not mistaken, and we can see on this graph that we have delta x, delta y, and we can draw our second line between these 2 points. And if we manage to reduce our delta x, you can see that second line will get closer and closer to graph. So difference between second line and some points. So for example, in this, their difference in graph and second line is quite big. So we can already see it on graph. but if we reduce delta x, quite soon we won't see difference between second line and graph in this point, and it will just get closer and closer. And now we can calculate our actually slope of function or slope of our tangent by dividing delta y on delta x. So we can draw the same on blackboard, like this is our second, and if we reduce difference between x2 and xy, then our graph will convert into and for example we want to get slope of our function, and if we are reducing difference, then we just get tangent. Which will have with graph only one common point, and this point is actually equal to x1, y1. And now we can introduce our derivative finally. So derivative can be introduced as slope of tangent. Derivative of f of x in point x is equal to slope of tangent. Which goes through points x and y, which has only one common point, and this point is x1, y1. So that's actually can be called a geometrical meaning of derivative. And now we will talk how to calculate derivative, and later why it's so useful. So, as we remember, slope of tangent is equal to f x1 plus delta x minus f x divided by delta x. It's the same which as these two expressions have the same meaning, but I just rewrote because this form is actually more simpler to understand. And we remember as delta x is getting closer to 0. And how to represent this? Delta x is getting closer to 0. So consider that you have a calculator, and you substitute, you have some, you know x, where you want to calculate derivative, and you just substitute delta x is equal to 1, calculate by this formula, then delta x is getting smaller and smaller. And in that case, our slope will get, for example, from 3 to 2 and 1, 2 and 0. So as delta x is getting smaller and smaller, if our function is not very strange and doesn't have some spikes or some other points where it just don't have meaning, our slope is getting closer and closer to some number, and as we can see, this number is 2. And that means that this number is derivative of some function in point x. And for better understanding, now we calculate derivative of several functions using this method. So first function we will start from is just constant. So consider you have and our y is equal to constant at every point x. So can you already say what derivative of this function is equal to at every point of this graph? So what do you think? 0. And why do you think? Can you prove this using, can you show? Because we've only considered geometrical meaning of function. So
we can't get any angle. If we draw the line, it doesn't touch the x line.
So that means that angle between graph and angle between axis OX is equal to 0, right? That's what you want to say. So indeed, no, we can call this a line, and angle between this x and this line is equal to 0 because these lines are in fact parallel. So let's prove this by doing this algebraic definition after we've considered geometrical meaning. So now we substitute this expression for our particular function. So we get that derivative, which is denoted like that. So we have our function, and we just have this symbol under. Let me write one more time. And now we can substitute our function. So what is the value of this function for x plus delta x? If we substitute in this function, which for all points in a numerical line has a value of constant, what is value of this function for x plus delta x? And for x? And no matter what delta x, because delta x is getting closer to 0, but it never actually reaches it. So we can continue this list on and on, and it will be smaller and smaller, but it won't be zero. It won't be zero. It can be quite hard to understand, but this delta x is always bigger to zero, bigger than zero, but it approaches it. So we get that 0 divided by some number, some positive number, which means that it's equal to 0. So now we can, and this fact can be written as, this is our constant. We use the same symbol, apostrophe, and we can write that this derivative is equal to 0. Now we are considering linear function. That actually reminds of what we do at the start of the lesson when we calculated just slope of this line. Now let's do practically the same. So we will write in brackets that delta x is approaching to 0. You can't just forget about where delta x is approaching to. And we can rewrite the same definition over and over. And now substitute for x plus delta x. So this is our x, and now we can substitute. And the same for x. We can clean up this expression a little bit, and we again get that this is not equal to 0. That means that there is no error, and that means that we just it is a fraction of some positive number over it's the same positive number. So this is equal to 1 k. And that means that we can write that for linear function, our derivative is equal to k. And here's more base fact that if we substitute now k is equal to 1 and b is equal to 0, then we will get that this is equal to 0, 1 multiplied by x plus 0, just x. So derivative of x is equal to x. Oh, sorry, 1. And also we can prove this fact again, because if we now substitute k is equal to 0 and b is equal to c, then we will get 0 multiplied by x is equal to 0 plus constant. So this is constant again, and we get that derivative constant is equal to 0, which corresponds with this expression well. So let me, in this angle, write all derivative we have found so far. Now we can consider quadratic function, which we talk about, because it's a non-linear function, which means that its slope is depends on x2 and x1, and that's why we will need it to calculate in that way again. So now we have quadratic function, and as delta x is approaching to 0, we will have that derivative of this function in point x is equal to we are substituting delta x and x is nullifying. Now we are delta x is common denominator, and again delta x divided by delta x is equal to 1. And we still have delta x, so we haven't get rid of it, but now we can remember that delta x is approaching to 0, but it's not 0. That's why if we have, for example, x is equal to 1 and delta x is like 1 millionth, then we will just cover this delta x and just forget about it, because we can always choose such small delta x that it won't interfere with our calculations in any way. So that means that delta x can be cancelled. We just get 2x. So right now I demonstrated a very important fact that our delta x can be considered as very, very small number, and if we get this case, then we can just get rid of it and forget about it. Now we can see this. Let's firstly see our quadratic function on graph, and see how our algebraic derivative corresponds to graph. So first, let's consider x is bigger than 0. In that case, we can see that our function is constantly increasing. That means that if we take x2 is bigger than x1, and if both x's are bigger than 0, then squares of this axis will not change the sign. So increases. And now we can substitute our x is bigger to 0 to our derivative, and we can see that 2x is bigger than 0, which means that derivative is bigger than 0. Now, if we have x is smaller than 0 for this domain, we can see that if that function is constantly decreasing, and if we take some again bigger x2 than x1, then x2 squared will be smaller than x1 squared. And that means that our function decreases. And again, if we take a look at our derivative, it's because x is smaller than 0, then the derivative is smaller than 0. Right? And now what will happen if x is equal to 0 in that case? In that case, our derivative is equal to 0, because we can substitute 0 and we will get 0. And actually it's quite an interesting point, because it's the lowest point on this graph, and that means that for if our derivative is bigger than 0, we can we can say that this point is quite interesting. So that means that these points are called extremums. And these are interesting points, but we will get to them maybe in 2 lessons later. But you will need to remember that this fact will appear quite soon, and it will appear quite usually. And the same can be said about this fact, that's why derivative can be more useful than actually a function, because if we know function and if we know sign of this function, then we can just tell if function is smaller or bigger than 0. But if we know derivative, then we know if function is decreasing or increasing. And in machine learning, it's very important to know not actually value, but the way how to get the smallest or the biggest value. And that's why, for example, if we want to get the biggest value, we want our function, and if our function increases, then that means that we can take just bigger axes and get bigger functions. And if our function is decreasing, then we can just take smaller axes and get bigger values of functions. So let's have a break, and after that we will calculate a bit more of derivatives, and then we will talk about optimization.